In this video, we're going to focus on word problems that involve similar polygons and similar solids. If two polygons are similar, then the corresponding angles or the angles at matching corners are congruent or of the same measure. As a result, the measures of the corresponding sides are proportional. Let's say we have two similar triangles. Let's call the sides of the larger triangle as A, B, and C, and the sides for the smaller triangle as X, Y, and Z. The angles at the same corners are the same. And then the ratio between two corresponding sides, for example, let's take the ratio between these sides of the larger triangle. So we have A over B. This should be equal to the ratio between the corresponding sides on the smaller triangle. So corresponding side for A is X, then corresponding side for B is Y. Now, if two solids are similar, then they are of the same shape, and then the corresponding dimensions or linear measures are proportional. Let's take, for example, two similar cylinders. Let's call the bigger cylinder as cylinder A, and then the smaller cylinder as cylinder B. Let's call the height of cylinder A as HA, and the radius as RA. And then for cylinder B, its height is HB, and then the radius is RB. They are similar if the ratio between the height is equal to the ratio between the corresponding radius. In addition, if we take the ratio between the surface area, this must be equal to the square of the ratio of the linear measures or the corresponding dimensions. And if we take the ratio between the volume, this must be equal to the cube of the ratio between the corresponding dimensions or linear measures. First one, a person is standing 24 feet away from a street light that is 25 feet tall. How tall is he if his shadow is 6 feet long? So, the best way to solve problems that involve geometric figures is to make a sketch. Let's say that this is the street light and then this is the person. The street light is 25 feet tall. The height of the person is unknown, so we can call this x feet. The person is standing 24 feet away from the street light, so this is measured as 24 feet. And because of the street light, the person casts a shadow that is 6 feet long. So we can connect the tip of the street light and the head of the person down to the ground And so this is the tip of the shadow, and the shadow is 6 feet long. As you can see, we have drawn a right triangle, two right triangles actually, and they are similar. They are similar because they are both right triangles, and then they share the same angle here. And because they share the same angle here, these two angles are also the same. We are asked to find the height of the person, so that would be x. To solve for x, we can take the ratio between x and this side, the base of the smaller right triangle, which is measured as 6 feet, and equate this ratio to the ratio between the corresponding sides on the larger right triangle. So the corresponding side for x is 25 feet, and the corresponding side for 6 is the sum between 6 and 24, which is the base of the larger right triangle. Solving for x, we get 5 feet. Next, the radius of a cylinder is increased by 20% and its height is decreased by 50%. How much is the decrease or increase in its original volume? Let's define the dimensions. Let's start with the original cylinder. So let's call the original radius as r sub o or RO, and then the original height as HO. Now, the radius of the new cylinder is 20% more, so that would be 1.2 RO, and then the height is 50% less, so that would be 0.5 HO. We are asked to find the decrease or increase in its original volume, so that would be the difference between the new volume and the original volume divided by the original volume. If we get a positive value, then it's an increase. If negative, then it's a decrease. Let's solve. Our working equation is the volume of the new cylinder minus the volume of the original cylinder divided by the volume of the original cylinder. We can rewrite this as Vn over Vo minus 1. Using the formula for the volume of the cylinder, we have pi radius of the new cylinder squared times the height of the new cylinder divided by pi radius of the original cylinder squared times the height of the original cylinder minus 1. And then using the given conditions that the new radius is equal to 1.2 RO, so 1.2 RO squared, and then the new height is 1.5 or 0.5 HO. This is all over pi RO squared times HO minus 1. We can cancel out common factors, pi RO squared and then HO, so that we are left with 1.2 squared times 0.5 divided by 1 minus 1. This is now equal to 0.72 minus 1, or that would be equal to negative 0.28. We have a negative value, so it's a decrease. And if we multiply this value to 100 to get the percent, therefore there is a 28% a decrease in its original volume. Next problem. A conical vessel has a height of 24 centimeters and a base diameter of 12 centimeters. It holds water to a depth of 18 centimeters above its vertex. Find the volume in cubic centimeters of its content. Alright, so let's make a sketch. Conical vessels are inverted cones. So the height of this conical vessel is 24 centimeters, and then the base diameter is 12 centimeters. It holds water to a depth of 18 centimeters above its vertex. So this is the vertex of our cone, and the depth of the water is 18 centimeters above this vertex. So the surface of the water is 18 centimeters above the vertex of the cone. We are asked to find the volume of the water inside the cone. We have two ways to solve this problem. Number one, we can solve for the radius of the water inside because it's unknown. Let's call that, for example, our W. Or we can just apply the formula that I mentioned earlier, taking the ratio of the volume, which is equal to the cube of the ratio between the known linear dimensions, in this case, the height. So let's use the latter approach, taking the ratio between the volume, let's say volume of the water over the volume of the cone, which is equal to the cube of the ratio between the known linear dimensions, again in this case the height. So height of the water inside, and then the height of the cone. Isolating the volume of the water, we get the volume of the cone times the quantity HW over HC cube. And then using the formula for the volume of the cone, which is 1/3 pi r squared height. So 1/3 pi, radius of the cone is 12 divided by 2, so 6 squared times the height of the cone is 24 centimeters times the height of the water, which is 18 centimeters, and height of the cone again is 24 centimeters, and this is cubed. Therefore, the volume of the water is equal to 381.70 cubic centimeters. Another way to solve the problem, as I mentioned earlier, is to solve first for the radius of the water inside. Let's say this is the radius of the water, and then plug in the value to the volume formula. We can solve for the radius by using similar polygons, in this case similar right triangles. So we can take the ratio between the radius of the water and the height of the water, 18 centimeters, and equate this to the ratio between the radius of the conical vessel, which is 12 divided by 2, so that would be 6, over the height of the conical vessel, which is 24 centimeters. So solving for the radius of the water, we get 4.5 centimeters. And then let's plug in this value to the formula for the volume of the water. So in this case, we'll be using the formula for volume of the cone. So volume of the water is equal to 1/3 by r squared. Radius of the water is 4.5, so 4.5 squared times height, in this case height of the water, which is 18. So solving for the volume of the water, we get 381.7 cubic centimeters.